I once wrote a migration script that corrupted over 2 million records worth of data, which almost crashed our production system. This took place sometimes in 2018. It's 9 a.m. Tuesday morning. I just woke up and had my first coffee when suddenly,
Yo, your are about to explode.
the Our platform engineer alerted us that our Kubernetes pod had been spiking in memory usage since last week. They were on the verge of crashing on prod. My tech lead and I dropped everything to investigate, and it wasn't so obvious even after digging through our Kibana logs and Datadog. After pulling out a ton of hair, we finally figured out the root cause of the memory issue. Needless to say, it was my fault. But first, you need to understand what my team was doing. For context, we were working on an online banking system. Well, more like a wrapper around another banking and payment solution. When I first joined the team, all user-sensitive data were stored in plain text. Yeah, don't ask me why. We got slapped for it and had to start encrypting user data before storing into our MongoDB. I of course couldn't live the easy life and wanted to get that sweet bonus so that Kiki can live his best life, so I volunteered to take on this task. After exploring various options, we decided to go with MongoDB client-side field-level encryption. Client-side field-level encryption is just a mechanism that encrypts sensitive data at the application level. Your application uses something like a master key that can be stored in something like AWS KMS. You then use this master key to encrypt another set of keys called the data keys. And MongoDB stores these encrypted data keys in a special collection called the key vault. When writing sensitive data, MongoDB drivers analyzes your query to detect if any encrypted fields are involved. If it finds that there's encrypted fields, the drivers then fetches the data key from the key vault, encrypts the query's values, and sends the encrypted query to MongoDB. With this pattern, even if your MongoDB is compromised, the attacker wouldn't be able to decrypt the data without having the master key. Okay, so now that you understand the gist of this, here's the migration strategy that we follow. Set up master key on KMS, done. Use a master key to generate data encryption key, done. Configure automatic encryption in our MongoDB connection, done. Next, we updated our Mongo schemas. For each sensitive field requiring encryption, we create another field with the suffix_encr. For example, user.name gets a new field called user.name_encr. We kept both fields in the schema so existing code could continue using the original field while we transition. Then we implemented pre-save hooks that automatically copy data from the original field to the encrypted field, and MongoDB driver will then encrypt it based on our configure schema. We also implemented getters that reads from the encrypted field first, falling back to the unencrypted field if the encrypted field doesn't exist. This allowed all existing unencrypted field references in our codebase to work seamlessly without modification. After deploying these code changes, we would run data migration scripts that iterated through all our existing documents and populate the encrypted field from the original fields. We had done this by collection to avoid overloading the database. Once confirmed that our apps were working correctly with the new encrypted field, we would run another set of cleanup migration to remove the original unencrypted field from all documents. Now here's where things went sideways. I wrote a migration script for the user collection, one of the most critical collection in our MongoDB database. Within the user model, we had a nested object called foreign tax info that contained the SIN number, that's social insurance number for us Canadians or social security number for you American. This is what the migration looked like. Retrieve all documents, set encrypted fields with the original field, and update. Feel free to pause the video to spot the bug. Were you able to find it? If you did, yes, I know it's stupid issue. I was young and dumb. I don't know what I was doing, okay? Here's what I thought would happen. The encrypted SIN number would be populated. But what actually happened was only the encrypted fields was saved and the unencrypted field was wiped out. Why? When you use a set operation with a nested object, MongoDB doesn't merge the properties. It replaces the entire object. And it got worse. We started running the migration, got about 80% through the collection, when another prod issue came up that required immediate attention. We had to stop the migration to handle the issue. We fixed that issue and the app was still running normally at this point. Remember the pre-hook that we implemented? It was able to continue to use the encrypted field through our application. We then ran the migration the second time against all record. I don't exactly remember why we did this instead of running it against the unencrypted documents only. My only assumption is that we thought we would be able to finish this in one go. This caused all our user records to have both the encrypted and unencrypted SIN number fields set to undefined. The migration tried to set the encrypted SIN field with the original SIN number, which had already been erased in the first run, resulting in both fields being undefined. So how did this almost cause our pods to crash? Okay, this part is a little bit foggy to me. It's been a very long time and I can't recall the exact details, but I remember we had an endpoint that was calling a find on a user collection with the SIN number being undefined. When you query MongoDB for field undefined, it essentially matches all documents where the fields doesn't exist or is explicitly set to undefined. So this query, which should have only returned one user, suddenly returned millions of records each time. And this was being called throughout the day, causing our pods to spike up so much in memory. Yep, so that was a dumb mistake that caused a lot of headache and that needed to be fixed ASAP. I'm not gonna lie, I was very lucky to have had help from so many different people. We've messaged our database engineer to restore a backup of our user collection on a different cluster. Unfortunately, we couldn't just restore the backup from a few hours ago because the data had already been set to undefined. We had to restore data a day before the migration first ran. That's perfect except for one thing. How the hell were we gonna get the list of users who had registered during the time at which we first ran the migration to now? Luckily, it turned out that every user's registration that happened also got sent to Redshift. Our data engineer were able to quickly generate a list of that users. With all the above data in place, we were able to recover all our user records on our database. Once done, we immediately saw a significant decrease in memory usage across our Kubernetes pod. Woof, thank God. We then just needed to fix the migration and rerun it. That was super embarrassing and caused so much headache to everybody. But at the same time, I was kind of proud of myself for owning up to that mistake and making sure that I was able to fix the problem with lots of help, and I learned so much from this mistake. Hey, if you made it this far, thank you so much for watching. Do you have any other prod issues that you can share with us? I would love to read them, and maybe your experience will help future software engineers as well. As always, thank you so much for watching, Happy New Year's, and see you in the next one.